So now we're going to talk about the simplest way of predicting what a branch does, and that is simply predicting the branch is not taken. And we'll see how well that works. So here's a pipeline with 3 delay slots, and let's see what happens when we predict not taken. So here's our branch. We go ahead and execute it. We're not going to find out what the branch does until we get to the memory stage in cycle 4. So during the time when we're waiting, we're going to go ahead and predict that the branch isn't taken. So we're going to go ahead and start executing the next instructions. By the time we find out if the branch is taken, we're all the way down here. So this means we've gone ahead and started executing a lot of instructions in the 3 cycles it takes to resolve the branch. So there are 3 cycles before we know what happens with the branch, and we've already started instructions here. So these instructions are going to go ahead and execute. And if we're correct that the branch is not taken, then these are the right instructions, and we've got great performance because we've had no branch delay slot and we've just kept executing. If we were wrong and the branch was taken, then these are the wrong instructions, and if we let them finish, we're going to do the wrong thing in our program and we'll cause the program to crash. So we need to make sure that if this was wrong, that we clean up the fact that we started the wrong instructions. And this is the problem with predicting a branch. If you predict incorrectly, you have to clean up. So let's take a look at predicting not taken. We're basically guessing that the branch will not be taken, and we keep executing instructions. So this is pretty straightforward. If we guess right, that is a correct prediction, then we have 0 branch delay. We get full performance out of our pipeline because we just keep going. However, if we guess wrong, then we have to go in and kill those instructions that were wrong to make sure the program runs correctly, and we suffer the delay. So we still had to wait for the branch to resolve itself. So we had to wait 3 cycles to find out what the answer was, and if we guessed wrong, we have to kill the instructions we did in that time and then start over at the right branch. So how do we kill the instructions? Well, we need to make sure they don't execute. If we execute the wrong instructions, then our processor is doing the wrong thing. The term for this is killing or squashing the instructions. To do that, we can either prevent them from writing, so we can disable the register write and the memory write in the pipeline, or we can turn them to no-ops. So we can change the instructions in the pipeline to no-ops. Remember, that's add R0, 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 and so as they go through the pipeline, they won't have any effect. But we need to make sure that we kill the wrong instructions, otherwise we're going to do the wrong thing in our processor. So let's see how this works when we predict not taken. So here's our branch. We determine it in this cycle, but we're going to go ahead and execute a bunch of instructions, predicting that the branch is not taken. When we finally figure out what happened, we discover that the branch was taken. So now we've got all these instructions that we went ahead and executed, and they're wrong. So because the branch was taken, we need to kill these instructions. These are the wrong instructions for the program, and so we're going to go through and make sure that we kill all the instructions in the pipeline that were the wrong ones to execute. So this is what we have to be able to do in order to be able to do branch prediction. So how well does this work? Well, let's look at some statistics. About 33% of branches are taken. So if we predict not taken, we're about 67% accurate. Is that good enough? Well, to see if that's good enough, we need to look at the performance penalty of predicting that accurately. So let's take a look at a modern Intel processor, a Nehalem processor. It has a branch misprediction cost of 17 cycles. That is, each time you predict a branch incorrectly, it costs you 17 cycles that you have to execute, you have to get rid of from your processor pipeline. So that's a lot of cycles to lose every time you predict a branch incorrectly. Now, we saw earlier that 17% of instructions are branches, and now let's work out what the cost here is. So we're predicting correctly 67% of the time for 17% of instructions that are branches, and every time we predict incorrectly, it costs us 17 cycles. So to figure out what the penalty here is, it's 17% of our branches, our instructions are branches, times 33% of the time we're going to mispredict the branch. And for each of those mispredictions, we're going to pay a 17 cycle penalty, plus we spend 1 cycle for every instruction we do correctly. So this is 1.95 cycles per instruction. So this is nearly 2 times slower, even though we're 67% accurate. So even predicting like this, even with 67% accuracy, predicting not taken is going to cause our processor to run about 2 times slower than it would have otherwise. So this is clearly not good enough. We can't have our processor running half as fast as it should just because we're not predicting accurately. So we need better ways to predict. So let's take a look at a question here. What is the performance penalty for predicting taken, as opposed to not taken, on the Nehalem processor? So same statistics as before, 17% of the instructions are branches, 33% of branches are taken, and the misprediction costs 17 cycles. Well, this is going to be 2.9 times slower, almost 3 times slower. So we had 17% of branches are instructions, and now we have 67% of the time we're mispredicting the branch. So we pay that 17 cycle penalty 67% of the time, and that's going to be 2.9 times slower.